Welcome to Deep Thinkers. Tonight, let yourself go somewhere impossibly old. Not last year, not 1,000 years ago, not even 1,000,000. Go back 4.5 billion years to a world that would look nothing like the one beneath you now. There is no name for the countries yet. There are no countries. There are no oceans in the shape you know them. No green. No soft blue haze at the edge of the sky. There is only a young planet, freshly made, still glowing in places, still deciding what it will become. And if you could stand upon it, you couldn't. But if you could, the very first thing you would notice, before the heat, before the strangeness of the air, is that the day would end far, far too soon. Because the day was only 5 hours long. Let that settle for a moment. Not 24 hours. 5. The young Earth spun so fast, whirled so quickly on its axis, that the sun would climb, race across the sky, and fall again in the time it now takes you to sleep half a night. A morning, a noon, an evening, a darkness, all of it compressed, hurried, breathless, the horizon turned like the rim of a spinning wheel. There was no such thing as a long, slow afternoon. There was no such thing as rest. The world was young, and it could not stop moving, and it would keep that frantic pace for a long, long time before anything came along to slow it down. And then there was the moon. You know the moon. You have seen it 1,000 nights, a pale coin hung high and small and calm. So far away that you can hide it behind your thumb held at arm's length. That is the moon of now. But the moon of that ancient sky was not small, and it was not calm, and it was not far. It hung close, 10 times closer, perhaps 20 times closer than it floats today. Not the familiar 384,000 kilometers of distance we measure now, but something closer to 20 or 30,000, a stone's throw, in the language of worlds. And so it did not look like a coin at all. It filled the sky. It loomed, a vast, glowing, molten-faced thing, so wide across the heavens that it swallowed whole regions of the dark. Close enough that you might have felt you could reach up and lay your palm against its cratered warmth. Picture a moonrise on that world, not the gentle silver lifting you have watched over a quiet field. Imagine a wall of light climbing over the edge of the earth, enormous, filling more of the sky than seems possible, a face so large it seems to press down upon the land. And as it rose, it pulled. It dragged the seas, such as they were, hot and restless and young, into tides that dwarf anything the modern world has ever known. Tides not of meters, but of something closer to 1,000 times higher than the tides you might watch lap at a shoreline today. Great heaving surges of water rushing far inland, then draining away, then rushing back, driven by that huge near-hanging moon, over and over, in the rhythm of a day only 5 hours long. It is an alien scene. It is almost impossible to hold in the mind a racing sun, a looming moon, colossal tides sweeping across a young and steaming world. And yet, this is the strange and beautiful thing. This is not some other planet in some other galaxy. This is here. This is home, in its infancy. Everything you love, every forest and coastline and quiet evening you have ever known, grew out of this. And all of it, the tides, the moon, the very tilt of the world that would one day give you seasons, all of it began with a single act of unimaginable violence. But we are getting ahead of ourselves. Breathe, let the racing world slow in your imagination, just for a moment, and let us turn to a quieter puzzle. Because before we speak of the violence, we should speak of the mystery it left behind. A mystery so strange that it nearly broke the whole story apart. Here it is. The moon, that pale companion of your nights, should not be what it is. And to understand why, we have to talk about what the moon is made of. For a long time, no one truly knew. People guessed. They looked up and wondered whether the moon was a sister world, born beside the earth from the same cloud of dust, or whether it was a wanderer, a stranger caught and held by the earth's gravity as it passed. There were many ideas, and we will come to them. But everything changed when human beings finally went there and brought pieces of it home. When the astronauts of the Apollo missions walked upon that grey and silent surface and gathered up rocks and carried them back down through the long dark and placed them at last under the patient eyes of scientists in laboratories, that is when the real mystery revealed itself. Because when they measured those moon rocks, atom by atom, element by element, they expected to find something foreign. Something with its own signature, its own fingerprint, marking it as a thing born elsewhere and separate. That is what everyone assumed they would see. Instead, they found something that made no sense at all. The moon was made of Earth. Not similar to Earth, not roughly like Earth. Almost identical to Earth, specifically to the outer rock of the Earth, the great deep shell of stone we call the mantle that lies beneath the thin skin of the crust. To understand how strange this is, you need to know a small thing about the atoms that make up rock. Certain elements come in slightly different versions of themselves, heavier and lighter twins. We call them isotopes, the same element wearing coats of slightly different weight. And here is the wonderful part. Different worlds, formed in different places in the young solar system, carry different blends of these isotope twins. It is a kind of chemical accent. A birthplace fingerprint. Mars has one accent. A distant asteroid has another. Each body, born of its own particular patch of the ancient cloud, speaks in its own subtle isotopic voice. And when the scientists listened to the accent of the moon rocks, the oxygen, the titanium, the chromium, the tungsten, all those subtle blends of heavy and light, they heard the voice of Earth. Not a cousin's voice, not a neighbour's, the same voice. So alike that even with the finest, most exacting instruments we possess, straining to find any difference at all, they could barely tell the two apart. The moon and the Earth's mantle spoke as one. Hold that thought gently, because it is the seed of everything strange to come. The moon is, chemically, almost the Earth's twin. And that, as we will see, is exactly what should not have happened. Why should it not have happened? Because of how we think the moon was born. And that is where the violence returns. But keep this puzzle warm in the back of your mind, like a coal you are unwilling to let go cold, because we will need it again. If the moon is made of Earth, where, then, is the world that struck us? Where did the attacker go? Remember the question. It waits for us at the end of this long night, and its answer is stranger than the puzzle itself. Now, before we go back to the collision, there is one more strange thing hidden in this story, and it lies not up in the sky, but far, far beneath you. Beneath the floor of the room where you are resting, beneath the foundations, the soil, the bedrock. Beneath the deepest mine humankind has ever dug, beneath the roots of the mountains, down and down, nearly 3,000 kilometers straight down, to a place no drill will ever reach. The boundary where the rock of the Earth's mantle finally gives way to the molten metal of the Earth's core. Down there, in that unreachable dark, there is something waiting. Two somethings. We cannot see them, of course. No eye has ever looked upon them, and no eye ever will. But we can hear them, in a way. When great earthquakes shudder through the planet, they send waves rippling through the whole body of the Earth, and those waves travel at different speeds through different kinds of rock, bending and slowing as they pass. And by listening patiently across the whole world to how these waves move through the deep, a kind of listening we call seismic tomography, which is really just the art of mapping the unseen insides of the Earth by the way that tremors pass through them, scientists have found two enormous shapes crouched at the base of the mantle. Two masses, each one continent-sized. Not the size of a mountain, not the size of a country, the size of a continent, thousands of kilometers across, rising up off the core like vast buried mountains of a strange and different stone. One sits beneath the continent of Africa, the other sits beneath the wide floor of the Pacific Ocean. Seismic waves slow down markedly as they pass through them, which tells us that these two masses are not like the rock around them. They are hotter or denser or made of something chemically different, set apart, foreign, other. For decades we did not know what they were. We still argue about it. But there is a new idea, a striking and haunting idea that we will build toward through this whole long night. And the idea is this, that these two buried masses, these continent-sized shapes hiding at the bottom of the world, may be the last remains of the vanished attacker, the grave of the world that built the moon. Sunk deep, and still down there, 4.5 billion years later, beneath your feet, tonight, but that is the end of the story, and we are only at the beginning. Let the buried shapes rest in the dark a while longer. Let us go back up through 3,000 kilometers of rock, up into the light of that fierce young sky, and ask the question that all of this has been circling. What actually happened? What was the act of violence that spun off a moon made of earth, that set the whole world tilting and turning toward the possibility of life, and that may have left two graves in the deep? To answer that, we must meet the idea that changed how we understand our own origins, and we must meet the ghost of a world that no longer exists. The idea is called the giant impact hypothesis. And like so many ideas that turn out to be true, it did not arrive all at once, in a single flash. It was built carefully by more than one mind over more than 1 year, out of the slow accumulation of evidence and the willingness to imagine something enormous. It began in the form we know it today, in the year 1975. Two scientists, William Hartmann and Donald Davis, put forward the notion that the moon was not a sister born beside the Earth, nor a wanderer captured from afar, but the child of a collision. That early in the history of the solar system, when the young planets were still forming and space was crowded with debris and half-finished worlds, something very large had struck the growing Earth, and the wreckage flung out from that blow had gathered itself together in orbit and become the moon. Then, just a year later, in 1976, two other scientists, Alistair Cameron and William Ward, arrived at much the same idea, working independently, coming at the problem from their own direction and reaching the same astonishing conclusion. The moon was born of impact. The moon was the scar of a catastrophe hung in the sky. Now, an idea like this needs a villain. It needs the thing that did the striking, the great body that came out of the dark and hit the young Earth. For years it was simply the impactor, a nameless world, a hypothetical intruder. But a thing without a name is hard to hold in the mind and hard to love, and a story wants a name. It was the geochemist Alasdair Halliday who gave it one, in the years around the turn of the millennium. And the name he chose was perfect. He called it Theia. Theia. Say it softly. It comes from the old Greek myths, from the age of the Titans, those elder gods who came before the gods of Olympus. Theia was a Titaness, and in the myths she was the mother of Selene, and Selene was the goddess of the moon. Do you see the beauty of it? The name says the whole story in a single breath. Theia, the mother, gave birth to the moon. The world that struck the earth was named for the mother of the moon goddess, because from the body of Theia the moon was born. A dead world, named for a mother, remembered forever in the child she left hanging in our sky. There is a tenderness in that, hidden inside a story of the most terrible violence imaginable. The thing that destroyed became the thing that created, and we gave it the name of a mother. So this is where the story truly opens, on the threshold of the catastrophe. A young Earth, spinning wildly, its day only 5 hours long, still hot from its own formation, still gathering itself out of the rubble of the newborn solar system. And somewhere out there in the crowded dark, on a slow and fatal course, another world, Theia, drifting toward an appointment 4.5 billion years in the keeping. Two worlds, moving toward a single point in space and a single moment in time, in the oldest and most violent chapter of the Earth's whole life. We have a name for that chapter too. We call it the Hadean Aeon, named for Hades, the lord of the underworld, the god of the dark below, because to those who named it. The Earth of that age was a kind of hell, a world of magma oceans and falling fire, of heat and bombardment and constant remaking. And it is in that hell, in that Hadean dark, that the moon and the seasons and the tides and everything that would one day make life possible were about to be forged in a single blow. We do not know the exact day. We cannot. But we can date the event, roughly, and the way we do it is a small marvel of patience all its own. Certain elements in rock decay over time, one turning slowly into another at a rate so steady you could set a clock by it, and so, by measuring how much of one has become the other, we can read the age of things far older than any memory. One such natural clock uses two elements, hafnium and tungsten, decaying one into the other over the deep ages, and by reading that clock in the oldest rocks we have, we can place the Great Collision at around 4.5 billion years ago. Somewhere in the span between 4.5 billion and a little before that. Most likely a mere 60 to 150 million years after the very first solid grains of the solar system had formed. Those first grains, the oldest solid things we know of, tiny inclusions rich in calcium and aluminum locked inside ancient meteorites, are dated to about 4.5 billion, the true birth cry of the solar system. And not so very long after that first cry, on the scale of worlds, the Earth met Theia. I want you to feel how young everything was. The sun itself was newborn, still settling into its long, steady burn. The planets were half-made, unfinished, some of them still swept by rings of leftover rubble, still growing by swallowing the smaller bodies that crossed their paths. The Earth was not yet the Earth. It was a molten, half-formed thing, wrapped in a scalding sky, turning too fast, hot to its heart. And Theia was roughly the size of Mars. Think of that. Not a stray boulder, not a mountain fallen from the sky. A world. About 6,700 kilometers across, roughly half the width of the Earth. Carrying something like 1/10 of the Earth's mass, a genuine planet in its own right, with its own core of iron sunk at its center, its own shell of rock wrapped around it, its own long slow fall through the dark toward the world it was about to destroy and remake. For a moment, before the blow, hold both of them in your mind. The young Earth, spinning, glowing, its 5-hour days flickering past. And Theia, silent, patient, enormous, closing the distance across the last stretch of empty space. Neither one knowing, for worlds do not know, that between them they were about to make the moon, and the seasons and the tides, and set in motion the long, strange, unlikely chain of events that would end 4.5 billion years later, with a mind resting in the dark, listening to this story, made of atoms that were forged in that very collision. Because that is the truth we are moving toward, slowly, all through this night. You are not separate from that catastrophe. You are its child, just as surely as the moon is. The tilt of the world that gives you spring and autumn, the tides that breathe against every shore, the very steadiness of the climate that let life take its unhurried billions of years to become something that could wonder about its own beginnings, all of it traces back to the meeting of these two worlds. The most violent instant in the history of the Earth was also the most creative. It did not end the world. It built the one you live in. And so we return, at last, to the puzzle we set down a little while ago, the coal we were keeping warm. If the moon is made of Earth, if it speaks with Earth's own chemical voice, so exactly that we can barely tell them apart, then something is deeply wrong with the simplest version of this story. Because if a whole other world, Theia, came and struck the Earth, and the moon was flung out of the wreckage, then the moon ought to be made largely of Theia. It ought to carry Theia's fingerprint, Theia's accent, the birthplace signature of that vanished other world. It ought to be, in its bones, a piece of the attacker. But it isn't. It is a piece of us. That is the crisis at the heart of this whole beautiful puzzle, and in a little while we will follow it all the way down. We will watch the collision itself in all its physical detail, the angle of the blow, the speed of it, the way solid rock turned to glowing vapour and the whole Earth was wrapped in a shining cloud, the way Theia's iron heart plunged inward and merged with our own. We will watch the wreckage gather itself in orbit with almost unbelievable speed and become the moon. And we will find, at last, the strange and elegant answer to why that moon should wear the face of the Earth instead of the face of the world that made it. But not yet. For now, simply rest in the scene. A young world turning too fast under a racing sun. A vast near moon not yet born. Two continent-sized shapes not yet buried in the deep. And out in the patient dark, a world named for a mother, falling silently toward the appointment that would give birth to everything. Let yourself sink toward that ancient sky. There is no hurry. The collision has waited 4.5 billion years to be told, and it will wait a little longer still, while you settle deeper into the quiet. And we go on together, slowly, into the oldest night the Earth has ever known. Close your eyes, if they are not already closed, and let the number itself do the settling. 5 hours. That was the whole of a day. Once. Not the working day, not the waking day. The entire turn of the world, sunrise to sunrise to sunrise, took about 5 hours. Picture that if you can, though picturing it is really a way of letting go of everything you know. The sun climbing, the sun falling, the dark and the light again, all of it wheeling overhead in the time it now takes you to sleep a single stretch of the night. The young Earth spun like that. It spun fast, far faster than it does today, a fevered top of molten rock and cooling crust. And nothing yet stood in the sky to slow it. There was no moon. Hold on to that for a moment, because it is stranger than it sounds. The sky over the Hadean Earth was an empty sky. No silver disk, no changing face, no soft tide pool threading through the water. Just that racing sun, and the heat and the dark coming so often it barely felt like dark at all. And then, when the moon did come, it came close, so close it hardly seems possible. Not the small far lantern you know, that pale coin you can cover with a thumbnail held at arm's length. In the beginning, the moon may have hung only 20, perhaps 30,000 kilometers away. 10 times closer than today. Maybe 20 times closer. Set that against the familiar figure, the 384,000 kilometers that separate us from the moon tonight, and you begin to feel the difference in your chest rather than your head. The newborn moon did not sit in the sky, it loomed. It filled a great swollen arc of the heavens, a huge and heavy presence, so near you might have believed you could fall upward into it. And it pulled. Oh, how it pulled! The tides it raised were not the gentle breathing of the sea you know, the slow lift and fall along a beach. They may have been 1,000 times higher, 1,000-fold. Great mountains of water heaved up beneath that enormous moon and dragged themselves across the young world, sweeping far inland, then draining away again, over and over, in the rhythm of a day that lasted only a handful of hours. Rise and fall, flood and retreat. A planet breathing hard and fast under the weight of the thing it had just made. That is the world we are going to. A 5-hour day, a moon like a second face pressed against the sky, tides like walls of water walking the shore. It is not a nightmare, though it has the scale of one. It is simply the truth of where we began, before things slowed, before things softened, before the long calm set in that made room for everything gentle that came after. Let it be enormous, and let it be far away. And let yourself rest inside its strangeness, the way you might rest inside a story you loved as a child, one whose ending you already trust. Now, back to the puzzle we left hanging, because it is the thread that runs through this entire quiet journey, and I want you to feel it settle into place before we go on. The moon is made of Earth, not roughly, not approximately, almost atom for atom. When the astronauts of the Apollo missions brought their boxes of grey lunar rock back across the emptiness and handed them to the laboratories, the scientists did what scientists do. They measured. They looked at the isotopes, those subtle variations in the weight of atoms that act like a fingerprint, like an accent, telling you where in the solar system a given piece of rock was born. Every world has its own signature. Mars has a Martian signature. The meteorites from the far reaches carry their own, each place its own faint accent written into the atoms, and the moon's accent was ours. Its oxygen isotopes matched the Earth's mantle to a precision that left the researchers almost uneasy. Titanium, the same. Chromium, the same. Tungsten, the same. Line them up beside the rocks of Earth, and you cannot tell them apart. At the finest resolution we possess, the moon is not a cousin, not a sibling of some other family. It is a piece of home. And this, gently, is exactly what should not have happened. This is the thing that nearly broke the whole theory in two. Because if a world named Theia came falling out of the dark and struck us, and the moon was flung from the wreck of that collision, then the numbers, the simulations, the honest mathematics of it all said the moon should be built mostly of Theia. 60%, 70, 80 even. It should carry the stranger's fingerprint, not ours. It should look, when you brought its rocks home and measured them, like the leftover of some other world. A foreign accent. A different birthplace written in the atoms. Instead it speaks with our voice. And so the scientists found themselves holding a mystery, dressed as an answer. They had a theory that explained almost everything: the moon's size, its tiny iron heart, its bone-dry chemistry, and yet at its center sat this one impossible fact. The moon is our twin. The attacker left behind a child that wears the mother's face. Sit with the wrongness of that, softly, the way you'd sit with a riddle just before sleep takes you. If the moon is made of Earth, then where, in all of this, is Theia? Where did the other world go? Keep that question. Let it drift down into the dark with you. We will answer it, and the answer is more beautiful than the puzzle, but the answer waits at the very bottom of this long night. And there is a great deal of gentle ground to cover before we reach it. Because here is the last shape I want to lay before you, before we begin the slow descent into the collision itself. 2,900 kilometers beneath the place where you are lying right now, at the very floor of the Earth's rocky mantle, where it meets the molten metal of the outer core, there are two things that should not be there. Two masses, continent-sized, one of them sitting far below Africa, the other far below the Pacific. We cannot see them with any eye. We found them by listening, by watching the way the trembling of distant earthquakes slows and bends as it passes through the deep. And the waves slow through these two regions in a way that says the rock there is different. Hotter, perhaps, denser, made of something not quite like the rest of the world around it, something that does not belong to the ordinary body of the planet. They have been down there the whole time. Beneath every city, beneath every ocean, beneath every creature that has ever lived and died on the surface, these two vast shapes have rested at the bottom of the mantle. Silent, patient, for longer than there have been continents to sit above them. And there is a thought, a new and startling thought, only lately spoken aloud, that these two buried masses are not random stains in the deep earth at all, that they are graves, that they are the sunken remains of the world that made the moon, that Theia never truly left us, that she came apart on impact, gave the sky its silver child, and let the heavy iron heart of her own body sink down and down through the glowing young earth until it came to rest against the core, where it lies to this hour. We are going to earn that ending. We are going to walk toward it slowly, and by the time we arrive it, will feel less like a shock and more like a homecoming. But you can carry the shape of it with you now, into the deeper quiet, the way you might carry the last line of a lullaby whose meaning you only understand as you are falling asleep. The moon is made of earth, and the world that made the moon may be sleeping in the earth still. So let us go back, all the way back, to the moment before the blow, to the very beginning of the idea itself, which did not arrive in a single flash, but was built, patiently, by careful minds across the long middle of the last century. In the year 1975, two scientists, William Hartmann and Donald Davis, set down the notion that a great impact might have thrown the material of the moon into the sky. And a year later, in 1976, working on their own, Alastair Cameron and William Ward arrived at much the same vision. Between them they had lit the lamp we still read by. And later, when the vanished impactor needed a name, the geochemist Alastair Hadean reached back into the old Greek stories and chose one with a quiet perfection to it. He called her Theia after the Titaness of myth. For in those old tales, Theia was the mother of Selene, the goddess of the moon. The mother of the moon. It could not have been named more truly, and she did not yet know she was falling. She had been travelling for a long time. That is the first thing to understand about Theia, and perhaps the most important. She did not appear from nowhere. She did not materialize in the path of the young Earth like some sudden obstacle thrown into the road. She was a world, fully formed, with her own history, her own molten interior, her own iron heart already settled at her center. She had been turning through the same neighborhood of the solar system for millions of years, following an orbit that was, for a long while, perfectly stable, perfectly its own. The young sun blazed at the center of everything. The young planets, still wearing the dust of their making, traced their slow rings around it. And somewhere in the inner solar system, two of those bodies, the proto-Earth and this other one, this wanderer we would much later call Theia, were sharing the same broad lane of the sky. To understand how a collision becomes inevitable, you have to spend a moment in the physics of orbital resonance, but I will keep it gentle, the way you might explain a tide to someone who has only ever seen still water. When two bodies orbit the same star at similar distances, their gravitational fields reach across the space between them and tug. Usually the tugging settles into a rhythm, a give and take that keeps both orbits stable. But sometimes the rhythm breaks. Sometimes one body drifts just a little too close, just a little too often, and the tugs start to amplify rather than cancel, the way a swing begins to fly when you push at exactly the right moment every time. Simulations suggest this is what happened with Theia. Her orbit drifted, the distances shrank. The gravitational conversation between the two worlds became not a negotiation, but a ratchet, pulling them closer by degrees across a span of time we can barely imagine. And then there was no more distance left. The numbers that describe Theia, when you look at them carefully, are somewhere between humbling and astonishing. She was roughly Mars-sized. Mars, for a sense of scale, sits there at about 6,700 kilometers across, half the width of the Earth. Think of the Earth as a watermelon and Theia as something closer to a grapefruit, not a pebble, not a pea. A real world with real mass, with a gravitational field strong enough that if you stood on her surface, you would feel the ground beneath you. Her mass was approximately 1/10 of Earth's. That is not a fragment, that is not a chip of rock, that is an entire planet. And her iron core had already separated from her mantle and sunk to her center, the same way iron separates in all the inner rocky worlds of the solar system, drawn down by gravity and by the heat of formation. Theia had differentiated in the technical language of planetary science, which is just a formal way of saying she had organized herself, the heavy things at the center, the lighter rocks above. She was structured. She was whole. She had, in whatever sense matters, arrived now. How do we know when this happened? The answer is written in the rocks, and it takes a particular kind of clock to read it, one built not from carbon, but from metal. The system planetary scientists use for events this ancient is called hafnium tungsten chronometry, and the logic of it is elegant once you slow down enough to feel it. Hafnium is a metal. A radioactive version of it, hafnium-182, decays into tungsten-182. And tungsten, when it gets the chance, strongly prefers to go where iron goes. It is what geochemists call siderophile, iron-loving. So here is the useful thing. When a planet is forming and its iron sinks to make a core, it sweeps most of the tungsten with it. The hafnium, which is not iron-loving, stays up in the rocky part, the mantle. And then the hafnium-182 keeps decaying, quietly on its own fixed schedule, into more tungsten-182, which is now trapped in the mantle because the iron has already left. The ratio of these two isotopes in the rocks tells you very precisely when the iron separated, when the core formed, when the planet, in other words, became itself. Reading those ratios in the Moon and in Earth's mantle, accounting for the collision and what it would have mixed, scientists have arrived at an age for the giant impact that falls somewhere between roughly 4.5 and 4.5 1 billion years ago. Most estimates cluster between about 4.47 and 4.5 1 billion years. That is 4,500 million years. The number is so large it resists imagination, so let me offer a smaller anchor instead. The oldest solid objects in the entire solar system, tiny crystalline grains called calcium-aluminum inclusions, the first things to condense from the solar nebula, date to 4.567 billion years ago. The solar system's very first solids, and the giant impact happened roughly 60 to 150 million years after that. Which sounds like a long gap, but on the time scale of planetary formation, it is almost immediate. By the time the Earth was geologically an infant, not even 3% of the solar system's age old, the most violent event in its history was already done. All of this happened inside what geologists call the Hadean eon. The name comes from Hades, the Greek underworld, which tells you something about what the early Earth looked like to the scientists who named this chapter of time. It ran from the formation of the Earth, around 4.56 billion years ago, to about 4 billion years ago, a span of roughly 500 million years that we have almost no direct rock record of, because the surface was too violent to preserve anything. What we know of the Hadean comes from isotope chemistry, from lunar samples, from meteorites, and from simulations. It is a chapter written largely in inference, in the gaps between measurements, in the math of what must have been. The Hadean Earth was not a welcoming place. It was a place of magma and bombardment and heat so extreme that the rock itself could not stay still, and right in the middle of that chaos, Theia fell. The approach would have been, by any measure, slow. Slow in the way that planetary bodies move, which is to say fast by any human standard, but gentle by the measure of atomic collisions or artillery. Simulations suggest Theia arrived at something close to 4 kilometers per second relative to the Earth. For reference, a rifle bullet travels roughly 1 kilometer per second. So 4 times a rifle bullet, which sounds fearsome, and it was. But in the context of planetary science, 4 kilometers per second is near what physicists call escape velocity for the Earth at that time. It is the speed of something that just barely fell in, a grazer rather than a sprinter. If Theia had been going much faster, she would have hit and blasted material away so violently that much of it escaped entirely. If she had been going much slower, she would have simply merged, swallowed whole, leaving no moon at all. 4 kilometers per second was, in some sense, exactly right. The angle matters too. Almost everything that would follow depends on the angle. The simulations, and here it is worth saying clearly that these details come from models, from the careful numerical work of planetary scientists running computer calculations that take weeks to execute on machines the size of rooms. The simulations suggest the blow was oblique. A glancing strike, not a head-on smash. Think of it as the difference between a car hitting a wall straight on and a car sideswiping a truck. The head-on collision stops everything dead. The sideswiping collision transfers angular momentum, it sets the struck vehicle spinning, and it sends material flying sideways rather than simply compressing into the target. For the moon to form, you need material to go sideways. You need the debris to enter orbit rather than simply rain back down. A glancing blow at roughly 4 kilometers per second, coming in at an angle that planetary scientists often describe as somewhere between a direct strike and a full graze, is precisely the kind of collision that would throw a thick ring of material into orbit while still delivering enough energy to vaporize an enormous fraction of both bodies. Vaporize, it is worth sitting with that word. We are accustomed, even in discussions of extreme violence, to thinking in terms of melting. Lava, magma, things that flow and glow. But the energy delivered by Theia's impact exceeded melting by an enormous margin. Rock does not simply go from solid to liquid under these conditions, it goes from liquid to gas, the silicate minerals that make up the bulk of both planets. The olivines and pyroxenes and feldspars, the stuff that mountains are made of, the stuff of the ocean floor and the deep crust, were superheated in a matter of minutes to temperatures of thousands of degrees, beyond the boiling point of rock, and they became vapor, not smoke, not steam. Vapor, a gas of silicon and magnesium and oxygen atoms, the fundamental ingredients of stone, floating free in a plasma so hot it glowed. For a period after the impact, the Earth was not a world with a surface. It was a rotating mass of molten and vaporized rock, a cloud of incandescent gas held together by its own gravity, radiating light into the dark of the early solar system. The sky, if you could have been there to see it, which you could not, because there was no sky in any sense we recognize, only the glowing body of the planet itself, would have been a furnace. Rock rain would have fallen in curtains. The light would have been orange and white and blindingly, cosmically intense. This was not a planet with a catastrophe on it. This was a catastrophe that had temporarily become a planet. And inside all of that, something was happening that would shape everything afterward. Theia's iron core, that dense, organized, metallic ball at her center, which she had spent millions of years assembling through the slow sorting of gravity and heat, did not stay a ball for long. As the two bodies merged and the surrounding rock vaporized and flew outward into the forming debris ring, Theia's iron plunged. It fell inward through the churning, glowing, gas-mixed chaos of what had been two separate planetary mantles, and it sank toward the center of the combined body. The process was not instantaneous in the way a coin drops through water, but on the timescale of planetary events it was extraordinarily fast, a matter of hours. Within hours of the impact, Theia's iron heart had found its way to the core of the Earth and merged with Earth's own iron reservoir. This matters for the moon we would get. The moon formed from the material that flew outward, the disk, the ring, the cloud of orbiting debris. And that material was drawn primarily from the outer parts of both bodies, the mantles, the rocky layers above the iron hearts. Theia's iron was gone, absorbed into the Earth's core, no longer available to go into orbit. The moon would form from what was left over, and what was left over was rock, silicate-rich, volatile-poor, iron-depleted mantle material. The moon we would eventually get would reflect this origin. It would have a very small iron core, only about 20% of its radius, compared to roughly 50% for the Earth. It would be rocky and bone-dry, and it would look, chemically, very much like the outer layers of the Earth. But we will come back to that puzzle, because it is one of the deepest puzzles in the whole story. And it deserves its own space to breathe. For now, stay outside, in the disk. The debris that entered orbit around the ravaged Earth was not uniformly distributed. It was not a tidy ring, not Saturn's elegant geometry. It was a churning, gravitationally complex cloud of particles ranging in size from individual atoms of vaporized rock to boulders the size of cities. All of it still searingly hot. All of it moving, all of it subject to the gravitational pull of the Earth below and the gravitational pull of every other piece of debris beside it. The cloud extended outward to what scientists call the Roche limit. The Roche limit is one of those concepts that rewards a moment of attention. It is named after the French astronomer Roche, who worked out the mathematics in the 19th century, and it describes the critical distance inside which a body held together only by its own gravity will be torn apart by the tidal forces of a larger body nearby. Any closer than this limit, and the far side of an object is pulled so much more weakly than the near side that the object literally falls apart, shredded by the difference. The rings of Saturn exist largely inside Saturn's Roche limit. The material there can never accumulate into moons because the tidal forces prevent it. Outside the Roche limit, gravity wins, and material can clump and grow. The debris cloud from Theia's impact extended partly inside and partly outside this critical distance, but the material outside the Roche limit was free to start accumulating, free to start finding itself pulled together by its own collective gravity, free to start becoming something new. And it did. The speed of what happened next is one of the facts that never fails to produce a small, quiet shock in anyone who sits with it long enough. Planetary formation in general is slow. The accretion of the Earth itself from the solar nebula took tens of millions of years. But the Moon did not take tens of millions of years. It did not take millions of years. It did not even take thousands of years in most models. The simulations suggest the Moon assembled from the debris ring in somewhere between a few decades and a few centuries, with some estimates extending to perhaps a few thousand years at the outer bound. On a geological timescale, the Moon appeared almost instantaneously. The event that created it lasted hours. The Moon it produced was there, coherent, orbiting, within what amounts to a geological eye blink. The reason for this startling speed is straightforward once you think about it. The debris was not scattered randomly across the entire inner solar system. It was concentrated in a ring around the Earth, close, dense, all of it already moving in roughly the same direction at roughly the same speed. Gravity did not have to reach across vast distances to pull it together. It was already together. The clumping was a matter of nearby particles attracting nearby particles, cascading from small aggregates to larger ones still, building with an efficiency that widespread nebular accretion can never achieve. It was not the slow assembly of a world from dispersed dust. It was more like a sandcastle collapsing upward. All the sand was already in one place, and it just needed permission to organize. The Moon that emerged from this rapid accretion was not the serene, cool, silver world we know. It was a world freshly born of fire. The surface of the newly formed Moon was covered in a global ocean of magma, not a patch of lava here or there. An ocean, a global magma ocean, hundreds of kilometers deep in places, stretching from pole to pole, with no solid crust anywhere on the entire sphere. The heat that drove this came from two sources working together: the kinetic energy of the accreting particles, which converted to heat as they struck and merged and built the Moon's body, and the radioactive decay of short-lived isotopes that were abundant in the early solar system and released enormous energy as they decayed. The young Moon was a ball of fire, and then it began to cool. Cooling takes time. Cooling takes millions of years. when the body in question is roughly 1/4 the diameter of the Earth and is sitting in the afterglow of the most violent event the solar system's inner planets had yet experienced. But the cooling was not simply a matter of the whole thing freezing uniformly from the outside in. As the magma ocean slowly lost heat to the darkness of space, the minerals that crystallize first, the minerals that solidify at the highest temperatures, began to settle out, sinking toward the bottom of the ocean. And then the minerals that crystallize at lower temperatures followed. And then, critically, came the feldspars. Feldspar is a family of minerals you would recognize if you looked at the granite of a kitchen countertop, the pale flecks in the grey and black speckled stone. In the moon's magma ocean, as temperatures dropped far enough, feldspar crystals began to form. And here is the thing about feldspar, the thing that matters for everything that followed. Feldspar is buoyant. It is less dense than the surrounding magma. So instead of sinking, the feldspar crystals floated. They rose through the cooling magma ocean and accumulated at the surface, layer by layer, building a crust from the top of the liquid ocean downward. The geological term for this particular flavor of feldspar is anorthosite, a rock made almost entirely of calcium-rich plagioclase feldspar, and the ancient crust of the moon is made of it. When you look at the bright, light-colored regions of the moon, the old rough terrain that lies between the dark volcanic plains we call the Maria, you are looking at anorthosite. You are looking at the scum that floated to the top of a global ocean of molten rock 4.5 billion years ago and hardened into a skin. Those ancient highlands, pale and battered and cratered beyond counting, are the oldest landscape in the Earth-Moon system. They are what the moon looked like when it was new, or nearly new, once the fire had quieted enough to permit a surface at all. The rocks of the lunar highlands, retrieved by the Apollo astronauts and analyzed in laboratories across the world, are some of the oldest objects any human hand has ever held, remnants of the first crust of a world born from catastrophe. There are thin, bright flashes of geology inside those samples that tell the story of the magma ocean, even without being told. The mineral compositions speak of temperatures that no surface rock should ever reach, of crystallization sequences that only make sense if you imagine an entire world liquid from surface to depth. They are a kind of testimony, locked-in crystal structure, of what it felt like to be the moon in the first few 100 million years of the solar system's life. Meanwhile, close below the forming crust, the deeper magma ocean was continuing its slower cooling and crystallization, with denser minerals settling toward the base. The moon was becoming internally differentiated the same way Theia had been, the same way the Earth had been, the heavy things falling and the light things rising. The world organizing itself by density into layers. At the very center, a small core, iron poor by the standards of the rocky planets. Because the iron had mostly gone with Theia's core into the Earth, was taking shape. Above it, a thick rocky mantle, and above that, the slowly thickening anorthosite crust, pale and ancient and wide. The moon was becoming the moon, and it was doing so at a distance we would find terrifying. The modern moon sits at a mean distance of roughly 384,000 kilometers from the Earth. That is about 30 Earth diameters. Far enough away that it appears as a disk roughly half a degree across in the sky, the same apparent size as the Sun, which is why total solar eclipses are possible, a coincidence so precise it feels staged, though it is simply the product of physics and timing. But the newborn moon was nothing like that distance away. It was perhaps 20,000 to 30,000 kilometers from the Earth's surface. Sometimes the estimates run a little higher, but the range is consistently somewhere in that neighborhood, roughly 10 to 20 times closer than the moon sits today. Do you want to know what the sky looked like? A moon 10 times closer appears not a little larger, but an enormous amount larger, because the apparent area of a disk increases with the square of its angular size. A moon 10 times closer is a moon that appears 100 times larger in area than the moon we know, not twice as big across, 10 times as wide across. The moon in that ancient sky was not a disk, it was a presence. It filled a substantial fraction of the sky from horizon to horizon, an orange and black and molten surfaced world so close you could have traced the edges of its magma flows with your eye. The gravity that it exerted on the earth below, on the still molten earth, on the rock vapor atmosphere, on whatever fragments of earlier material had not yet been swept up, was enormous, immediate, physical. The tides it raised were not the gentle meter-high swells we know, which crest and fall twice a day and make the sea retreat and return in a rhythm that seems almost polite. The tides the newborn moon raised were hundreds of meters high, perhaps more, perhaps thousands of times higher than today's tides, sweeping across whatever surface existed with a force that would have made the ground shake as the water moved. But there was no ordinary water yet. The ocean tides we think of when we think of tides came later, when water was present in significant quantities and when the surface had cooled enough for liquid to persist. In those first moments, the tidal forces were working on molten rock, stretching and distorting the magma, raising solid tides in the crust as it tried to form, cracking and reshaping whatever attempted to stabilize. The moon was not a gentle neighbor in those early years. It was a gravitational engine pressing its full weight against the body of the Earth at extraordinarily close range, and the Earth, for its part, was spinning so fast that the concept of a day would have been almost meaningless by our standards. Before the impact, before the moon, simulations suggest Earth was already spinning with a day somewhere around that range. But after the impact, after all the angular momentum of Theia's oblique blow had been folded into the combined system, the Earth was spinning with a day of roughly 5 to 6 hours. The sun rose in the east and set in the west in the span of time that modern humans spend at work. Twice the light and twice the dark, and twice again, all in a single modern day. The sky moved so quickly that if you could have watched the stars, which you could not, because there were no stars visible through the rock vapor atmosphere and the glow of the magma surface, they would have wheeled overhead with a rapidity that made the whole sky seem in motion. 5 hours from sunrise to sunrise, 5 hours from high tide to high tide, 5 hours over and over in the howling, glowing chaos of the Hadean. And slowly, very slowly, on the timescale of hundreds of millions of years, it began to change. The mechanism of that change is called tidal friction, and it is still operating today, which is why I know you will find it easy to believe. When the moon raises a tidal bulge on the Earth, a slight elongation of the planet's body toward the moon, that bulge does not sit directly beneath the moon. Because the Earth is rotating faster than the moon orbits. The bulge is carried slightly ahead of the moon by Earth's spin, the way a wave slightly leads the boat that makes it. The moon's gravity pulls on that displaced bulge, and the pull is at a slight angle, backward on the bulge, trying to drag it into alignment, trying to slow the Earth's rotation, and forward on the Moon, trying to pull it into a higher orbit. Energy and angular momentum are transferred from the Earth's spin to the Moon's orbit. Earth slows. The Moon climbs outward. The day grows longer. The Moon moves farther away. This is still happening. Right now, as you lie still and your breathing slows, the Moon is moving away from the Earth at a rate of 3.8 centimeters per year. It is an extraordinarily precise number, and it is not guessed at or modelled. It is measured directly using laser beams. The Apollo astronauts left corner cube reflectors on the surface of the Moon, small arrays of precisely angled mirrors designed to send an incoming laser beam directly back in the direction it came from. Observatories on Earth still fire laser pulses at the Moon and time how long the light takes to return. The round trip, divided by 2 and multiplied by the speed of light, gives the distance to the Moon with a precision of millimeters. And when those distances are compared over years and decades, the Moon's retreat is unmistakable. 3.8 centimeters per year. Every year the Moon is farther than the year before, which means every year the day is a little longer. The rate at which Earth's rotation is slowing is something like 1.7 milliseconds per century, too small to notice in a human lifetime, but over geological time it accumulates into the chasm between a 5-hour Hadean day and a 24-hour modern one. The whole journey from 5 hours to 24 has been driven by the same mechanism that is still, quietly, working now. The Moon started close, slowing the Earth. It is still far, still slowing it. By the time you are rested and the morning comes, the Moon will be a fraction of a hair's breadth farther away than it was when you closed your eyes. The universe does not pause. But we are getting ahead of the story, and there is something that needs to be addressed before we can proceed comfortably. Because there is a problem. A deep, genuine, troubling problem that waited in the lunar samples brought back by the Apollo astronauts, samples that were supposed to confirm the giant impact hypothesis in glowing, triumphant terms, and instead delivered what some scientists quietly called a crisis. It begins with oxygen. Oxygen atoms come in different flavors, different masses, depending on how many neutrons are packed into the nucleus alongside the protons. The common version has 8 protons and 8 neutrons. One heavier version has 9 neutrons, another has 10. These variants are called isotopes, and their relative proportions, how much of each flavor exists in a given rock, are like a fingerprint. Different bodies in the solar system formed from material at different distances from the Sun, with different histories, and they have different oxygen isotope ratios. Mars rocks, when they fall to Earth as meteorites, have a recognizably Martian oxygen signature. Asteroid rocks have their own. The Earth has its own. These signatures are stable over billions of years and are not easily altered by heating or pressure. When the Apollo samples came back and the oxygen isotopes were measured, they matched the Earth's mantle. Not approximately. Not loosely. Almost exactly, with a precision that pushed the edge of the instruments used to measure them. The titanium ratios matched. The chromium ratios matched. The tungsten ratios matched within the uncertainties of the measurements. The Moon was, to the finest resolution that analytical chemistry could achieve, made of the same stuff as the Earth. And that was a problem. Because the classic giant impact models predicted that the Moon should be made mostly of Theia, 60 to 80% Theia's material, in many of the early simulations. If Theia was a separate world that formed at a different distance from the Sun or from a different part of the solar nebula, she should have had a different isotopic fingerprint. The moon should have looked, chemically, like a piece of a foreign world. It should have been detectably alien. It was not. The isotopic crisis, as it came to be called, did not kill the giant impact hypothesis. The hypothesis explained too many other things too well to simply discard, but it forced a reckoning. Either Theia was, against substantial odds, essentially identical in composition to the Earth, perhaps because she formed at essentially the same distance from the Sun and from the same population of material. Or the impact was not the kind of glancing blow that leaves most of Theia in the moon, but something more violent, something that mixed the two bodies so thoroughly that the distinction between Earth and Theia essentially disappeared. And it is the second of those possibilities that a pair of scientists named Simon Locke and Sarah Stewart spent years working out in careful, patient detail. Their proposal, published in 2017, is one of the more remarkable ideas in modern planetary science, and it bears a name that sounds almost whimsical, but describes something physically precise. They called it a synestia. The synestia is what you get when two planetary-scale bodies collide with enough energy that a large fraction of the combined mass is vaporized, not just melted, but vaporized. And the whole system is spinning so fast that it cannot maintain the shape of a planet. Instead of a sphere with a ring of debris around it, a synestia is a single connected structure, part planet at the center, part disk of molten and vaporized rock at the edges, all of it rotating together as one continuous body, bulging at the equator so dramatically that it forms a shape, something like a donut or like a spinning top, at the moment it loses its axis. There is no clear boundary between planet and ring. It is all one thing, a vast, roiling, incandescent cloud of mixed Earth and Theia material, held together by its own gravity, turning inside a synestia. The mixing is complete. The material that was Earth's mantle and the material that was Theia's mantle are blended throughout the entire structure. The way cream mixes into coffee when you stir vigorously enough. The isotopic signatures of the two original worlds dissolve into a single signature. And when the moon condenses out of this blended material, when enough of the cloud cools and accumulates and coalesces into the new orbiting body, it inherits the mixed signature of the synestia as a whole, not the separate signature of one parent or the other. Which is why the moon looks like the Earth. Because it is the Earth, or very nearly, blended and reborn. Locke and Stewart's work depended on detailed computer simulations, smoothed particle hydrodynamics, a technique that models fluid behavior by tracking the behavior of individual particles and summing their interactions, and on an enormous amount of careful thermodynamic modeling of how rock behaves at the temperatures and pressures involved. Their names belong on the list of the careful minds who have built our picture of this event, alongside William Hartmann and Donald Davis, alongside Alistair Cameron and William Ward, alongside Robin Canup, whose earlier and still deeply influential models of the giant impact had established the canonical picture that Locke and Stewart were now extending and revising. The synestia is not the only explanation for the isotopic match. There is another possibility, offered by Raluca Rufu and Oded Aharonson and their colleagues around the same time, not one Theia striking once, but a series of smaller bodies, a sequence of impacts over time, each throwing a moonlet into orbit, each moonlet carrying material drawn primarily from the Earth's mantle because Earth was the larger body in each encounter. Over time, the moonlets accumulate and merge into a single moon, one built almost entirely from Earth-derived material, with no isotopic distinction from the Earth because the Earth was its overwhelming source. The multiple impact hypothesis. It gives a different path to the same answer. Both ideas remain active areas of research. Both take seriously the thing that the Apollo samples made undeniable. Whatever happened, the moon's chemistry is Earth's chemistry, and any theory that does not account for that fact is incomplete. But here is something the moon's chemistry reveals about its birth that requires no theoretical controversy, because it is written straightforwardly in what is present and what is absent. The moon is extraordinarily dry. Bone dry, in the language planetary scientists sometimes use. The volatile elements, the elements and compounds that escape easily into vapor at high temperatures, things like water, potassium, sodium, zinc, are dramatically depleted in lunar rocks compared to Earth rocks of comparable composition. Whatever the moon formed from, it was hot enough and for long enough that these substances simply boiled away into space, never to return. They could not condense back fast enough. They were lost. This is exactly what you would expect from a birth in vaporized rock. The synestia, if that is what happened, would have been hot enough to drive off every volatile constituent. A magma ocean moon, cooling from a hot accretion disk, would have lost its volatiles in the same way. The dryness of the moon is a fossil of its fiery origin, preserved in the mineral ratios of every sample ever brought back to Earth. And the moon's small iron core, that 20% of radius figure, is the same kind of fossil. It reflects where the moon's material came from. Not from the deep interiors of planets where the iron lives, but from the outer layers, the mantles, the rocky parts. Theia's iron sank into the Earth. Earth's iron was already in the Earth's core, unavailable to go into orbit. What went into orbit was mantle material, and mantle material is iron poor. The moon that formed from it is iron poor. The proportions match the theory. What does not quite match the theory, what required the synestia and the multiple impact hypotheses to explain, is the chemical similarity between the moon and the Earth. But in every other respect, the moon's composition tells the story of its origin with a directness that leaves little room for doubt. It is a child of vaporized rock, born in fire, stripped of its water before it had water to lose, with an iron core too small for its size, because the iron went elsewhere specifically into the Earth. And there it sits, Theia's iron, merged with Earth's iron, deep in the core of the planet. Inaccessible, invisible, indistinguishable now from the Earth's own iron, after 4.5 billion years of mixing and churning. We cannot point to a specific portion of the core and say, that is Theia's. The mixing was too complete, too ancient, too thorough. But we can say with confidence that some fraction of what lies at the center of the Earth, that spinning ball of liquid and solid iron that generates the magnetic field, sheltering all of us from the solar wind, was once the heart of another world. It came from somewhere else. It fell through the vapor and the chaos of the worst day this planet ever had. And it sank, and it stayed. The question, though, the question that has been sitting quietly at the edge of everything since the beginning, is whether the iron core was the only part of Theia that stayed. Whether some portion of her mantle, some remnant of her rocky bulk that did not go into orbit, did not fully mix with the Earth's mantle, did not disperse and dissolve into the general chaos of the Hadean interior. Whether some of Theia might still be here. inside the Earth, not in the core, but in the mantle, intact or nearly so, a tombstone in rock. That is the question that carries us forward. And the answer that one team of scientists proposed in a paper published in the journal Nature in November of 2023 is the kind of answer that, once you hear it, makes everything else about this story feel like it was always leading here. But we are not quite there yet. Before we can stand at the base of the mantle and look at what two different research teams working with seismic data and computer simulations now think they may have found, we need to understand what the collision left behind above ground. We need to understand the machinery it installed, the systems that turned a catastrophe into a cradle, the axial tilt, the stabilizing moon, the tides moving across a cooling Earth in a rhythm that some scientists think may have had something to do with the beginning of life. We need to understand, in other words, not just what the impact was, but what it built, what it made possible, what it saved, by destroying almost everything first. The moon was there the whole time. It had been there before the Hadean eon finished cooling, before the first ocean settled, before the first microbe found a way to metabolize something and began the long experiment of life. It had been orbiting, receding centimeter by centimeter. Through every extinction and every flowering of complexity the Earth would ever know. And it held a secret that took us billions of years to notice. A secret written in the very atoms of its rocks. A secret that nearly unraveled the most successful origin story planetary science had ever built. You have to go back to the years after Apollo to understand why the secret was a problem. Not the impact itself, that happened in the Hadean. But the discovery of the problem happened in laboratories, in the years after those missions returned their cargo of lunar samples to the Earth. 12 men had walked on the moon between 1969 and 1972. They collected rocks. They brought them home in sealed containers, transported them by spacecraft and helicopter and truck to facilities where scientists in clean rooms waited with the kind of patient precision that a planet's story demands. The rocks were examined. Of course they were examined. These were the first pieces of another world that most human beings alive at the time had ever seen. And the scientists who examined them expected to find something foreign, something distinctly lunar, distinctly not Earth, something that looked, chemically and isotopically, like a world that had formed somewhere else in the solar system and arrived here through a cataclysmic collision. What they found instead was deeply strange. The oxygen in the lunar samples was, isotopically, almost identical to the oxygen in Earth's mantle rocks. Not similar, not close. Identical within the precision of the measurements, which kept improving over the decades as analytical tools got sharper. When scientists examined the titanium, the story was the same: lunar titanium and Earth's titanium, indistinguishable at high precision. Chromium, the same. Tungsten, the same. The moon was not a foreign visitor. Chemically speaking, it was made of Earth, made of something so close to Earth's own mantle material that you could not tell them apart. And here is why that was a problem. The giant impact hypothesis, the model that Hartmann and Davis had proposed, that Cameron and Ward had independently developed, predicted something specific about the moon's composition. In the version of the impact those early computer simulations described, the moon was built mostly from Theia's material. 60 to 80% of the debris that went into orbit and assembled into the moon should have come from the impactor itself, from that Mars-sized wandering world. Not from the Earth. But Theia was a different planet, a planet that formed in a different part of the solar system at a slightly different distance from the Sun, from a slightly different mixture of primordial dust and ice and metal. Different worlds have different isotopic fingerprints. We know this from studying meteorites. The rocks that fall to Earth from the asteroid belt carry clear, measurable isotopic signatures that allow us to distinguish where in the solar system they originated. Mars has a different oxygen isotope ratio than Earth. The asteroid Vesta has a different ratio than Mars. The Moon should have had a ratio somewhere between Earth and wherever Theia came from, if Theia was a different world and the Moon was mostly made of Theia. Instead, the Moon had Earth's ratio. That mismatch has a name in the scientific literature, the isotopic crisis. And for a long time it was genuinely threatening to the giant impact hypothesis. Not fatal, but threatening. Because there were ways to explain it away, and scientists are uncomfortable when their best theory needs a lot of explaining away. One explanation was straightforward, if uneasy. Maybe Theia just happened to have the same isotopic composition as the Earth. Maybe the two planets formed at similar distances from the Sun, from the same local reservoir of material, and so they were isotopic twins before they ever collided. Some models of planetary formation allow for this. If planets sweep up material from a wide feeding zone as they grow, they can end up with averaged-out compositions that look similar to their neighbors. On this reading, the isotopic match is a coincidence of planetary birth, and the classic impact model works fine, but the coincidence requires a very specific kind of planetary formation history. And the more precisely scientists measured the isotopic ratios as instruments improved through the 1990s and 2000s and 2010s, the more identical the Moon and Earth's mantle looked. Not just similar, nearly perfect twins. The coincidence would have to be exact. And exact coincidences make scientists uncomfortable in a particular way, because exact coincidences have a habit of turning out to be not coincidences at all. The other explanation was more radical. What if the collision was so violent, so energetic, so thorough in its physical mixing, that Theia and the Earth didn't stay as two separate blobs of material with their own identities? What if the impact was catastrophic enough to destroy both objects as distinct chemical reservoirs, to vaporize so much rock from both bodies, to blend them so completely inside a churning, superheated plasma of silicate vapor that the Moon, which later condensed out of that cloud, inherited a composition that was neither Theia's nor Earth's alone, but a true mixture of both. A mixture so complete that any trace of Theia's original isotopic signature was erased. That idea, that thorough mixing, could explain the isotopic crisis, was present in the conversation for years. But it needed a mechanism. The standard giant impact models, developed through the 1990s and 2000s by researchers like Robin Canup, described an impact energetic enough to melt both bodies, energetic enough to fling a disk of molten rock into orbit. In Canup's canonical 2001 and 2012 models, the collision is violent in the way a demolition is violent. It breaks things, it scatters material. But the two objects retain some separateness as they merge. The Earth ends up as Earth, somewhat larger. The Moon forms from the orbiting disk, which is mostly Theia. The mixing is incomplete. In 2017, two researchers named Simon Locke and Sarah Stewart proposed something different. They called it the synestia. The name is built from Greek roots, syn for together, Hestia for the goddess of the hearth, though the hearth in question here bore little resemblance to anything domestic. A synestia is what happens when a planetary body is hit so hard, at such an angle that the entire structure of the planet is obliterated as a solid object. The energy of the impact does not just melt the rock, it vaporizes it. Both bodies, or large fractions of both, are converted into a single enormous mass of superheated vapor and droplets, spinning so fast and glowing so brightly that the concept of a planet temporarily stops making sense. There is no surface. There is no core you can point to. There is a cloud. A vast, rotating, doughnut-shaped cloud of what used to be two planets, so thoroughly mixed that the boundary between them has literally ceased to exist. Take a moment with that. A planet is not just a large rock, it is a structured object, with a core and a mantle and a crust, each layer with its own chemistry. In a synestia, that structure dissolves. The Earth's mantle and Theia's mantle are not two piles of material sitting side by side. They are vapor molecules moving through the same turbulent, glowing cloud, indistinguishable from each other at the atomic level. And as the cloud eventually cools, as it begins to lose energy and condense, the moon that forms out of it inherits this fully mixed composition. It looks like Earth because it is a blend of Earth and Theia so complete that the original components are chemically unrecoverable. That is the synestia solution. An elegant one, not because it saves the theory at any cost, but because it is physically coherent. The mixing happens for a reason grounded in orbital mechanics and thermodynamics, not as an ad hoc adjustment. If the impact was energetic enough and the angular momentum was right, synestia formation is what the physics predicts. Locke and Stewart's 2017 models showed that the moon could condense from such a structure in a way that naturally explains the isotopic match. Think of it like this: if you take two very different colored dyes and pour them both into a blender running at full speed, what comes out is not striped. What comes out is a single new color that carries no trace of either original. The synestia was the blender. It is worth pausing here to appreciate what Robin Canup had done in the years leading up to this. Her work, the simulations developed through the 2001 and 2012 papers, was foundational in establishing the quantitative backbone of the giant impact hypothesis. She and her colleagues showed how the impact geometry, the mass of the impactor, and the pre-impact rotation state of Earth could conspire to produce a disk of the right mass and composition to form a moon like ours. The synestia model of Locke and Stewart didn't erase that work. It extended it into a higher energy regime that the earlier models hadn't fully explored. Both are part of the same evolving portrait of one event. And then there was another proposal offered that same year, 2017, by a different team. Raluca Rufu and Oded Aharonson, with their colleagues, proposed what is now called the multiple impact hypothesis. Instead of one large Theia striking Earth once and producing the Moon in a single violent event, they suggested a series of smaller bodies struck the early Earth over time, each impact spinning off a small moonlet into orbit. Those moonlets gradually coalesced over thousands or millions of years, drawn together by mutual gravitational attraction and orbital dynamics, until they assembled into the single large moon we see today. The multiple impact hypothesis carries its own elegance. If many different small impactors contributed to the moon's formation, and if each of those impactors came from the same general region of the solar system as the Earth, the same local reservoir of material that fed Earth's own growth, then the moon's isotopic similarity to Earth becomes less of a puzzle. No single Theia needed to be improbably Earth-like in composition. Each small impactor was just local Earth-like material added to the pile, one strike at a time. The scientific community has not settled conclusively on which version is correct: the single energetic Theia, the synestia, the multiple impacts. These models are still in conversation with each other, still being tested against increasingly precise measurements of lunar samples and computer simulations alike. The isotopic crisis is not a closed case. But the crucial point, the point that matters most for this story, is that the Moon's near-perfect chemical kinship with Earth is no longer an embarrassment for the giant impact hypothesis. It has become, instead, one of its most interesting features. A puzzle that drives the physics deeper, that opens the question of how completely two worlds can be blended when enough energy is applied. Because whatever happened in those first hours and days after the collision, whether the mixing was a synestia or something closer to Knupp's canonical merger or a sequence of smaller impacts, it happened in conditions of heat almost beyond comprehension. And those conditions left their fingerprints on the Moon. Fingerprints that the lunar rocks carry to this day. Fingerprints we can read. Here is one. The Moon is bone dry. Not dry the way a desert is dry. A desert still has water molecules locked in minerals, humidity drifting through it from distant oceans. The Moon is dry in a way most places in the universe are not. It is depleted of volatile elements, the atoms and molecules with low boiling points, the ones that vaporize easily when temperatures rise. Water, obviously, but also potassium, sodium, zinc. These elements appear in Earth's rocks in certain proportions. In the lunar samples brought back by Apollo, they are depleted, not missing entirely, not zero, but significantly lower than in the corresponding Earth rocks. The Moon formed in an environment hot enough that those elements, instead of being incorporated into the cooling material, simply boiled away. They were lost to space. What was left was the refractory residue, the atoms and molecules that survive extreme heat without vaporizing. And the Moon condensed from those survivors. Think of it like boiling a pot of soup and letting it reduce too long. The water is gone. The volatile aromatics are gone. What remains is concentrated, dense, shorn of its lighter components. The Moon is that reduction, born from the residue of temperatures that stripped away everything that could be stripped away. That depletion is a signature. It says, I was born in a fireball, I was born in a cloud of vaporized rock, and the heat was real, and it lasted long enough to drive off everything that could be lost. There is a second fingerprint written in the Moon's interior. The Moon has an iron core. Of course it does. Iron is dense, and even in a Moon formed from chaotic debris, iron sinks toward the center over time. But the Moon's iron core is unusually small. It makes up only about 20% of the Moon's radius. 20%. Earth's iron core accounts for roughly 50% of Earth's radius, half the diameter of the whole planet. The Moon is iron poor. Not iron-free, but noticeably short of the metal relative to what you would expect for a rocky body of its size. This, too, is explained by the impact. Iron is dense, and dense things sink. When Theia struck, and when the merged body was a churning sea of molten and vaporized rock, the iron drained toward the center. Theia's iron core plunged inward within hours and merged with Earth's core, as we have already traced. Deep, locked away, gone. The debris that went into orbit to form the Moon was overwhelmingly material from the outer layers of both bodies, the rock of the mantle, not the iron of the core. Earth's mantle had already been depleted of its iron before the impact because Earth's own core formation had happened earlier. So the disk of debris that assembled into the moon was rock-rich and iron-poor, and the moon that formed from that disk inherited that chemistry. 20% iron core versus 50%. The number is an echo of an impact that separated iron from rock, sent the rock into orbit, and left the moon as a monument to its own metallic poverty. When you look at the moon's composition, you are reading the record of the collision as surely as you would read a footprint left in soft ground. Now take a step back. Think about what you are actually looking at when you look up at the moon. That object, pale, enormous, unmistakable in the night sky, is not just a moon. It is not just a piece of debris that happened to end up in orbit. It is the anomaly of the solar system's inner planets. There is nothing else like it in our neighborhood. Mercury has no moon at all. Venus has none. Mars has two, but they are tiny captured asteroids, small irregular rocks, probably a few kilometers across, nothing remotely like the moon. The moon is a quarter of Earth's diameter, 1/81st of Earth's mass. Those numbers don't sound spectacular in isolation, but in context they are extraordinary. Among the rocky inner planets, moons are either absent or negligibly small. The Earth's moon is a major object in its own right, anomalously, improbably, remarkably large. That anomaly is itself a prediction of the giant impact hypothesis. A random capture event, if it happened at all, would most likely produce a much smaller satellite. Two planets co-forming from the same cloud of material rarely produce a satellite a quarter the size of the primary. But a giant impact, the right size, the right energy, the right oblique geometry, that is exactly the kind of event that throws enough mass into orbit to build something this large. The moon's anomalous size is not an embarrassment for the impact hypothesis. It is one of its strongest predictions, quietly confirmed every time you look up. And that size matters enormously for everything that follows. A large moon, much larger than any other moon the rocky planets have, exerts a large gravitational influence. Not just on the tides, though that influence is real and consequential, but on something subtler, something deeper in the physics of planetary dynamics. Something that, once you understand it, makes the moon's formation look less like a catastrophe and more like the installation of a system. A long-running, slow-acting, planet-steadying system. But before it could begin that work, the moon had to do one more thing. It had to lock. Tidal locking. The phrase sounds mechanical, and it is. It describes a specific gravitational process by which one body's rotation is brought into synchrony with its orbit around another. Here is how it works. Earth's gravity pulls slightly harder on the near side of the moon than on the far side it has to, because the near side is closer. This differential pull raises a tidal bulge in the moon's rock. Not in an ocean, the moon has no ocean, in the rock itself. Solid rock, flexed by gravity into a very slightly elongated shape, almost imperceptibly if you are looking with human eyes, but completely perceptible to the mathematics. In the moon's early days, it rotated faster than it orbited. It was a newly formed object with its own angular momentum, spinning relatively quickly. As it spun, the tidal bulge that Earth's gravity raised in the moon's rock was constantly being dragged forward of the Earth-Moon line, then pulled back toward alignment, then dragged forward again. That constant flexing dissipated energy. The energy came from the moon's rotation. And as the moon lost rotational energy to that constant tidal flexing, it slowed down. Century by century, millennium by millennium, it slowed, until eventually its rotation rate matched its orbital rate exactly. One rotation per orbit. Always the same face toward Earth. That is the state the moon has been in for billions of years. Tidally locked, synchronized, the near side, the side you have looked at every time you have looked at the moon in your entire life, is the only face Earth ever sees. The far side, sometimes called the dark side in popular usage, though it is not actually dark, it receives exactly as much sunlight as the near side, is a hemisphere that no human eyes saw directly until 1959, when a Soviet spacecraft photographed it for the first time. Tidal locking is born of the impact. The moon formed with a certain spin, and the tidal relationship with the Earth gradually modified that spin over millions of years until it settled into perfect synchrony. The locking is a fingerprint too, a record of a long gravitational conversation between two bodies at close range, gradually arriving at a rhythm that has been maintained for so long that it now feels like a natural feature of the cosmos. The moon shows us its face. It has always shown us this face. It will show us this face for as long as the Earth and the moon remain close enough to each other to maintain their gravitational dialogue. And that gravitational dialogue, that intimate, enduring coupling, is the machinery we need to understand. Because the moon's size, its mass, its distance, its slow monthly orbit, all of those numbers combine to produce something that no other rocky planet in the inner solar system possesses. Something that, it turns out, may have been as essential to the emergence of complex life as liquid water or breathable air. Something the Earth almost certainly would not have had if it had not suffered that catastrophic collision 4.5 billion years ago. The moon is not just the Earth's companion, it is, in a very specific physical sense, the Earth's keeper. To understand what it keeps and what would happen if it were not there, you have to think about the way a planet spins. About what keeps a planet tilted, about the relationship between axial tilt and the seasons, between stable seasons and stable climate, between stable climate and the long, slow, patient process by which simple chemistry becomes complicated chemistry, becomes life, becomes complex life, becomes the incomprehensible variety of organisms that have covered this planet for the last 500 million years. All of that took time, enormous amounts of time, and the time was only available because conditions stayed stable enough for long enough, which is not guaranteed, which is, in fact, far from guaranteed on a planet without a large moon. Which is something that would not become clear until 1993, when a French planetary scientist named Jacques Lascar, working with his colleagues, published a set of calculations that quietly reshaped how we think about the conditions necessary for life. But we are not quite there yet. Before Lascar, before the axial tilt and the stabilizing mechanics and the question of what would happen to Earth's seasons in a universe without the moon, before all of that, there is still one more piece of what the impact built that needs to be laid out. One more consequence that connects the violence of the Hadean to the question of where life came from. The tides. Not the gentle twice-daily rhythms of the modern ocean, though those matter too. The tides of the Hadean Earth, when the moon was not at its current distance of 384,000 kilometers, but instead hung at perhaps 20,000 to 30,000 kilometers away, 10 to 20 times closer, an object that loomed in the sky in a way our moon does not and cannot anymore. At that distance, the tidal forces acting on the Earth's oceans and solid surface were not a gentle flexing. They were enormous. The tidal range, the difference between high tide and low tide, could have been hundreds of meters in some models. The tides swept far inland, not lapping at a beach, but racing across a landscape of bare volcanic rock and cooling lava fields. And they retreated, and they swept in again, with a periodicity driven by that close, fast-moving moon completing its orbit in hours, not a month. Those tides were not just dramatic scenery, they were chemistry in motion. Every time the tide came in, it carried whatever molecules had dissolved in the early ocean, amino acids perhaps, or nucleotides, or simpler organic compounds delivered by the late veneer of infalling asteroids, or built from the chemistry of hydrothermal vents and volcanic gases. Every time the tide went out, it left those molecules behind in pools, concentrated them, allowed the water to evaporate in the heat, thickened the soup. Then the tide came back. And repeated, over and over, on a cycle driven by the moon's close orbit, a cycle of wetting and drying that some researchers have looked at and thought, that is exactly the kind of repeated concentration and dilution and reaction cycle that chemistry might need to cross the threshold from molecules to something self-replicating. It is important to be careful here. The tidal pool origin of life hypothesis is a hypothesis. It is not established. It is not something the scientific community has converged on as the explanation for how life began. The origin of life is one of the most genuinely open questions in all of science, and there are many competing ideas: hydrothermal vents, ice-covered oceans, cometary delivery, atmospheric chemistry. The tidal pools are one possibility among several, attractive and physically motivated, but not proven. What can be said with confidence is that the conditions created by a close moon, those enormous tides, that repeated cycling of wet and dry, were real, were chemical, and were unlike anything the Earth has experienced since that early epoch. Whether they were necessary for life to begin or merely coincident with it remains unknown. But they were there. What is certain is that the tides were powered by the moon, and the moon was powered by the impact, and the impact was the event that set the whole chain in motion. However life began on Earth, it began on a planet that had been profoundly shaped by the collision. It began in an ocean that was being moved by the gravity of a world that owed its existence to Theia. That connection runs under every origin of life story, even the ones that don't mention the moon at all. And while those early tides swept across the cooling Hadean landscape, something else was happening, something that is easier to measure, because its consequences are still unfolding today, in real time, with instruments precise enough to detect the change. The moon was moving away, 3.8 centimeters per year. That is the current rate of recession, measured with instruments of extraordinary precision, lasers fired from Earth, bounced off the arrays of retroreflectors that Apollo astronauts placed on the lunar surface, their return times clocked to nanoseconds. The distance calculated and recalculated over decades of observation. The number is not an estimate, it is a measurement, and it encodes within itself the record of what has already happened over the 4.5 billion years since the moon formed. 3.8 centimeters per year. Across 4.5 billion years, that adds up. The moon was not always where it is. It started much closer, 20 or 30,000 kilometers, looming in that alien Hadean sky. And as it receded, the tidal coupling between the Earth and the moon transferred angular momentum from the Earth's spin to the moon's orbit. the moon's orbit grew. The Earth's spin slowed. 5 hours. 6 hours. The Earth's day, when it was young, passing in that brief interval, a day you could barely call a day, in which the light would barely have time to warm anything before darkness returned. Now 24 hours. And still slowing by about 1.7 milliseconds per century, a number so small it is unnoticeable in any human experience. But real, confirmed, and still accumulating. The moon is receding, and the day is still lengthening. Both changes driven by the same underlying physics, the same tidal exchange of energy that began in the first hours after the moon assembled from its disk of debris. These are not disconnected facts. They are the same fact viewed from different angles. The moon took energy from the Earth's rotation and spent it on its own orbit. That energy budget is why the tides were titanic in the Hadean and are merely impressive today. It is why the day went from 5 hours to 24. It is why the moon sits where it sits, at its current distance, in its familiar monthly track across the sky. And as it moves away, slowly, over timescales that dwarf the age of our civilization, its influence on the Earth will gradually, imperceptibly diminish. The tides will weaken. The gyroscopic grip on the Earth's axial tilt will ease. The stable wobble that is now held within a reliable range will, in the deep future, be freer to wander. Not in any timescale that matters to us, or to any likely descendant of civilization. But the moon's stabilizing influence is not a permanent gift. It is a loan, whose terms were set 4.5 billion years ago, and which will eventually be called in by nothing more dramatic than the patient arithmetic of orbital mechanics. There is something quietly remarkable about that. The same physics that drove the moon away also drove the day from 5 hours to 24, and will eventually drive the moon far enough away that it no longer holds the tilt as firmly. The price of having the moon slow the Earth was always going to be the moon's eventual distance. The stabilization was always finite. That impermanence is itself a piece of the story. The collision gave the Earth a keeper, but gave it with an expiration date written into the physics from the first moment of formation. We are living in the window. And to understand what that means, to understand the full weight of what the moon's presence has done across billions of years, we need to sit with the question of what the Earth would look like without it. Not as a thought experiment for its own sake, but because the contrast is what makes the impact's true legacy legible. The quiet catastrophe that didn't happen because of the catastrophe that did. Jacques Lascar's 1993 calculations pointed at exactly that. At the moon's absence, at the mathematics of what Earth's axial tilt would do, given millions of years and the gravitational perturbations of the other planets, if there were no large moon to resist them. The answer, and we are just arriving at the threshold of it, is the kind of answer that once you take it in, changes the way you look at every familiar thing on Earth's surface. Every forest, every ocean current, every creature adapted to a particular season in a particular place. The moon is why those seasons exist. The moon is why they are stable. And the stability of those seasons, maintained across billions of years, is the quiet gift at the center of everything this story has been building toward. Lascar's work is where we go next, and with it, the full measure of what a single oblique collision, a Mars-sized body striking the young Earth at roughly 4 kilometers per second, about 4.5 billion years ago, actually installed inside this planet and above it. What it made possible, what it saved, by very nearly ending everything first. Jacques Lascar was a mathematician at the Paris Observatory, and in 1993 he published a set of calculations that, in planetary science circles, had something of the quality of a quiet revelation, not a dramatic overturning of consensus, but rather the slow kind of understanding that arrives when someone does the work of following a thread to its end. What he found, when he ran the mathematics of Earth's axial tilt forward and backward through deep time, was that the Moon is not incidental to the planet's climate. The Moon is the climate's hinge. To understand what that means, you need to sit with what the axial tilt actually is. Right now, as the Earth circles the Sun, it does not stand perfectly upright. It leans. The angle between Earth's rotational axis and a line drawn perpendicular to its orbital plane is about 23.5 degrees, 23.4 more precisely. That lean is the reason the northern hemisphere tips toward the Sun in June and away from it in December. That lean is why there are summers and winters, why there are springs and autumns, why the seasons exist at all. Take the lean away, point Earth perfectly upright, and you get a world of monotonous, unvarying day length at every latitude, no meaningful seasonal cycle, no annual rhythm of warming and cooling, a different planet almost completely. The 23.5 degrees was not deliberately chosen, it was set by the impact. When Theia struck the proto-Earth at that oblique angle, at roughly 4 kilometers per second, the combined angular momentum of both bodies was folded into the new system. The spin rate changed, the orientation changed. The planet was left tilted, like a top that has been nudged partway over but not knocked flat. And that tilt encoded something remarkable into the planet's future, the possibility of seasons, the annual rhythmic redistribution of sunlight across latitude, the cycling of temperature that drives ocean currents and atmospheric circulation, and the migration of organisms and the growth of organisms, and, on a long enough timescale, the evolution of organisms. The impact set the tilt set the rhythm. The rhythm is the drum the whole living world dances to. But here is the thing that Lascar understood that most of us do not instinctively appreciate. A tilt is not a fixed thing. The Earth is not rigid in space. It is spinning, like a gyroscope, and gyroscopes precess, they wobble, slowly, around the axis of the forces acting on them. The Sun and the Moon and the other planets all pull on the Earth with their gravity, tugging especially at the slight bulge around the equator that centrifugal force has built up. Those tugs, accumulated over thousands and millions of years, have the potential to shift the axial tilt, to make the lean more extreme or less, or to send it wandering across a wide range of values. For the Earth as it actually is, with a large moon overhead, this wandering is small. The current tilt varies only slightly, oscillating through a range of about 1 1/3 degrees around its mean value over a cycle of tens of thousands of years. That small wobble is itself significant. It is one of the Milankovitch cycles, the orbital rhythms that pace the ice ages. But it is a contained wobble. Controlled, the Moon's gravitational grip on Earth's equatorial bulge acts as a kind of damper, a gyroscopic anchor, resisting the tugs that would otherwise send the tilt, drifting far from where it is. What Lascar's calculations showed is what happens when you remove that anchor, when you run the simulation of Earth without a large moon, subject to the gravitational perturbations of Venus and Jupiter and the rest. You do not get a planet with a slightly more variable tilt. You get a planet where the tilt is chaotic. where it can swing over millions of years through an enormous range, from values near 0 degrees to values approaching 85 degrees or more, with no periodicity, no predictability, no stable mean to return to. Just a wandering axis, driven by the accumulated gravitational influences of the solar system's other bodies, with nothing large and close enough to resist them. Try to feel the planetary consequences of that. A tilt near 0 means almost no seasons. A tilt near 85 degrees means something almost too extreme to visualize. A planet where the poles point nearly at the sun for half the year and then swing away in the other half, where the equatorial regions cycle between blazing heat and deep cold, where the jet streams and ocean currents and precipitation patterns would shift and reverse on timescales that no complex biological system could track. A planet that experienced that kind of variability would not necessarily be lifeless, but it would make the evolutionary stability that gave rise to complex multicellular organisms, to nervous systems, to brains, to the entire slow flowering of consciousness on this world. It would make all of that vastly harder, perhaps impossible over the billions of years it actually required. That is the scale of what the moon's stabilizing presence represents. Not just a convenience, not just a tide raiser, a guardian of the tilt that gave the planet its seasons. And those seasons, held stable enough for long enough, are part of what let life do what it needed to do. It is worth pausing here to acknowledge that Laskar's extreme result, that range from near 0 to 85 degrees, has been examined and debated in the decades since 1993. Some researchers have argued that the actual range of instability in a moon-free scenario might be somewhat less catastrophic than the original calculations suggested. The precise numbers remain an active area of inquiry, but the central finding, that Earth's axial tilt is dramatically more stable with a large moon than it would be without one, holds. The direction of the conclusion is not in doubt, even if the magnitude of the moon-free chaos is still being refined. The moon stabilizes the tilt. That much is solid. And the tilt, right now, is 23.5 degrees, held there, gently rocking within its 1 1/3 degrees of variation, year after year, century after century, kept steady by a world that was built from a catastrophe 4.5 billion years ago and has been doing its quiet work ever since. The moon does not only hold the tilt, it also pulls the ocean. The tides are one of those phenomena that are so constant, so woven into the texture of the world as it is, that it can be easy to forget they are not simply a feature of the ocean itself, but an effect, a consequence, a long-reaching arm of that ancient gravitational bond between the Earth and the Moon that was established in the first chaotic centuries after the impact. The Moon's gravity stretches the ocean into a slight ellipse, pulling the side facing the Moon toward it and allowing the side facing away to bulge outward in the other direction. As the Earth rotates beneath these bulges, the water rises and falls, the tides. Twice a day, more or less, at most coastlines, a few meters of difference, typically predictable enough to schedule ferry crossings and navigate harbours. But the tides we experience today are, in the context of this story, a faint echo, a ghost of what the early Earth knew. Consider the distances. Today, the Moon sits about 384,000 kilometers from Earth. In the early period after the impact, the Moon was forming far closer, perhaps only 20 to 30,000 kilometers away, 10 to 20 times closer. That change in distance matters enormously, because gravitational force does not scale linearly with proximity. It scales with the square of the distance. A moon 10 times closer would have exerted gravitational forces on the ocean roughly 100 times stronger than today. The tides in the young ocean, if there was a coherent ocean yet, which is itself a matter of debate, would have been on a scale almost impossible to picture from the world we know. Sweeping inland, reshaping coastlines not annually but within hours. The rhythmic violence of water on a scale closer to geological sculpting than to what we call a tide. And the day was short. The early Earth, spun up by the momentum of the collision, was rotating far faster than it does now. Before the moon existed to slow it, models suggest the day was somewhere between 4 and 6 hours long. Call it roughly 5. 5 hours from sunrise to sunset. A year still lasted a year. The orbital period around the Sun is set by the Sun's gravity and the Earth's orbital distance, not by its spin rate, but that year contained not 365 days, but something closer to 1,000 of them, each one a brief flicker of light and dark. You can try to picture a Hadean morning. The sun rises, crosses an arc of sky in what feels like a sprint, sets again. In the few hours of that compressed day, a moon that looms enormous on the horizon, far larger in apparent size than we see today, is pulling water across the young surface with an almost unbearable force. There are no continents yet, not as we know them. The crust is thin. The interior is largely molten. The air is thick with nitrogen and carbon dioxide and water vapor, and whatever volatiles have not yet been stripped away. Nothing lives, nothing has ever lived, and yet the machinery that will eventually make life possible is already running, already doing its work. The moon is slowing the spin. Every tide carries a small amount of rotational energy away from the planet and deposits it into the moon's orbital motion. This is a process that has been measured, not inferred, not modelled, not calculated on paper, measured. Among the instruments left on the lunar surface by the Apollo missions were small corner cube reflectors, arrays of prisms designed to bounce laser pulses back to Earth. Since the early 1970s, astronomers on the ground have been firing laser pulses at those reflectors and timing how long it takes for the light to return. Because the speed of light is known with extraordinary precision, the round-trip time gives the distance to the moon with centimetre accuracy. And when you do this month after month, year after year, decade after decade, a trend emerges. The moon is moving away from the Earth at a rate of about 3.8 centimetres per year. Not fast enough to notice in a human lifetime, not fast enough to notice in 1,000 human lifetimes. But real, steady, measured, that recession is tidal friction made visible. The energy that keeps the moon climbing away from Earth is coming from the Earth's spin. As the moon recedes, the spin slows, the day lengthens. It lengthens slowly, by something like 1.5 to 2 milliseconds per century, depending on the state of the ocean basins and how efficiently they transfer tidal energy. But over 4.5 billion years, that accumulation has added up to everything. From a 5-hour day to the 24-hour day we know, and the process has not stopped. The day is still lengthening, still being stretched by the same mechanism that has always stretched it. If you could wait long enough, far longer than our sun's remaining life, the day would eventually lengthen until the Earth showed the same face to the moon always, locked in mutual synchrony the way the moon is already locked to us. For now, we are somewhere in the middle. A 24-hour day, A moon at its current distance, still receding, still slowing the spin, still damping the tidal energy that 4.5 billion years ago was crashing across a Hadean world in waves as tall as cliffs. There is a hypothesis, genuinely fascinating, genuinely unproven, that those early tides may have done something more specific than sculpt shorelines. The idea is that the rhythmic wet-dry cycles in tidal pools, driven by tides on the young Earth, could have created ideal conditions for the concentration and chemistry of organic molecules. The basic logic is not hard to follow. Shallow pools, alternately flooded with seawater and then exposed to the air, would have seen the repeated concentration and evaporation of dissolved molecules, a natural cycling that mimics, on a large scale and with enormous energy, some of the processes that researchers use in the laboratory to drive chemical reactions. The theory holds that this kind of environment might have been where certain critical molecular assemblies first began to form, where the chemistry of life started to organize itself. This is worth saying clearly, this is a hypothesis. An attractive one, with smart researchers working on it, consistent with other things we know about early Earth chemistry. But not established. Not proven. The origin of life remains one of the most genuinely open questions in science. The moment where we know approximately what had to happen, biochemically, but not where it happened or precisely how the transition was made. The tidal pool hypothesis is one of several serious proposals. Hydrothermal vents on the ocean floor are another. The specific setting for the origin of life is not settled. What can be said is that whatever setting it was, the moon was part of the context. The moon built the tidal environment. The moon was slowing the day, raising the water, cycling the coastlines. The whole chemical theatre of the early Earth was running under a sky dominated by a moon far larger than any we have ever seen. And that moon, even if it was not directly stirring the pot of life's first chemistry, was shaping the physical conditions in which that chemistry had to happen. The moon that built the conditions is slowly leaving, 3.8 centimeters per year. In the deep future, millions of years out, far beyond the sun's expected lifetime, the moon will have receded to a distance where its grip on Earth's tilt is weaker, where the stabilization that Lasker calculated begins to loosen. The window we are living in, the window of stable seasons and manageable tides, and a 24-hour rhythm that every organism on this planet has calibrated its biology to, is not permanent. It is a long-duration gift that came with an expiration. The moon is leaving. And as it goes, slowly, over time, far longer than any we can intuitively hold, the machinery it installed will begin to wind down. We are living in the window. That is what was meant before. The window opened 4.5 billion years ago when a Mars-sized body struck the young Earth and threw debris into orbit. The window has been open since then, providing stable axial tilt, providing tides, providing a 24-hour day that suits the circadian rhythms of every living thing. And the window, one day, will close. But before it closes, before we leave this part of the story for the last one, there is something remaining to account for. A thread that has been running beneath this whole narration, seeded in the earliest parts and never quite paid off. The question of where Theia went. The iron core merged with Earth's core within hours of the impact. That much was noted. The outer material, the mantle rock and vaporized silicate, was blown outward, mixed in the roiling chaos of the synestia, and eventually coalesced into the moon. But the mixing was never perfect. No mixing ever is. And for decades, the assumption was essentially that Theia was dissolved, disaggregated, absorbed, that the impactor was simply incorporated into the new combined system and ceased to exist as anything separately identifiable. That assumption may be wrong. In November of 2023, a paper appeared in the journal Nature. The lead author was Qian Yuan, a researcher who was then at Arizona State University and later moved to Caltech. The paper proposed something that, when you first read it, has the quality of a good story that turns out to be true, or at least might be. The paper proposed that the two largest structures in Earth's deep interior, the continent-sized anomalies sitting at the base of the mantle, nearly 3,000 kilometers beneath the surface, are not ordinary mantle material at all. They are, the paper argues, what remains of Theia. Those anomalies have been known by seismologists for decades. They have a name, large low-shear velocity provinces, that does not lend itself to easy imagery, which is why in practice they are often called simply the blobs. There are two of them. One sits beneath Africa. The other sits beneath the Pacific Ocean. Each one is enormous, thousands of kilometers across and rising up to 1,000 kilometers or more off the core mantle boundary. Together, they are the largest distinct structures in Earth's interior by a significant margin. Seismic waves, the ripples that move through the planet's interior after earthquakes, travel at different speeds through different materials depending on those materials' temperature, density, and composition. When seismic waves pass through the blobs, they slow down, noticeably, measurably, in a way that tells seismologists that the material there is different from the mantle that surrounds it, hotter or denser or both, chemically distinct. They are not uniform mantle rock. They are something else, sitting at the planet's deepest interior boundary, above the liquid iron outer core, persistent and stable, and for decades unexplained. Various explanations have been offered over the years. Some researchers have proposed that the blobs are dense pockets of ancient, undepleted mantle material that survived from the planet's earliest history without being recycled. Others have suggested they represent accumulations of former ocean floor, old oceanic crust that subducted into the mantle over billions of years and collected at the bottom. These are serious proposals from serious scientists, and the debate is far from resolved. The blobs are real. What they are made of and why they are there is not settled. What Qian Yuan and his colleagues added to that debate in 2023 was a specific, quantitative, physically coherent proposal that the blobs are made of Theia. Their simulations used a method called smoothed particle hydrodynamics, a way of modeling fluids and near-fluid materials as collections of interacting particles, each carrying properties like density and temperature and composition. When they simulated what would happen to the dense, iron-rich chunks of Theia's mantle during the impact, they found that the material's density was the key. Theia's mantle, in their models, was roughly 2 to 3.5% denser than Earth's surrounding mantle. Not dramatically denser, but enough. Dense material in the mantle sinks. Not quickly. The mantle is effectively solid on human timescales, though it flows like an extremely slow fluid over geological time. But over millions of years, material that is denser than its surroundings will gradually settle downward toward the core mantle boundary. Theia's mantle fragments, in Yuan's simulations, sank through the molten, churning interior of the young Earth and accumulated at the bottom. And crucially, the density difference was enough to keep them there. The surrounding mantle could not easily mix them back in. They stayed coherent, not as sharp fragments, not with clean boundaries, but as two large piles of chemically distinct material, separated roughly into the two hemispheres by the geometry of the mantle's convection patterns. If this is right, and the caveat must be repeated because it is not yet consensus, then Theia did not fully leave. The iron core merged, the outer layers became the moon. But a significant portion of the impactor's mantle sank to the bottom of the Earth and has been sitting there ever since, for 4.5 billion years, through all the subsequent history of the planet. Through the formation of the continents, the evolution of the atmosphere, the emergence of life, the long procession of species across the surface. Beneath all of it, two continent-sized masses of another world. A grave that was also a beginning. The implications do not stop at the level of the poetic. The blobs are not inert. The core mantle boundary is the source region for certain kinds of mantle plumes, rising columns of unusually hot rock that punch upward through the mantle and eventually feed volcanic hotspots at the surface. The large igneous provinces, the massive flood basalt events that have punctuated Earth's history and in some cases contributed to extinction-level environmental changes, may be connected to the behavior of material at the core mantle boundary. The supercontinent cycle, the rhythm by which the continents drift together and then apart over hundreds of millions of years, may be influenced by the way mantle convection interacts with the structures at the base of the mantle. If the blobs are Theia, then Theia may still be shaping the geology of the surface world, not passively stored at the bottom of the planet, but actively influencing what happens above. That thought arrives slowly if you let it. The world you are living on, the surface under every city and every forest and every ocean, is being influenced in ways that can be traced back, if Yuan and his colleagues are right, to the moment of the impact. Theia did not only assemble the moon out of ejected debris. Theia installed the tilt, stabilizing moon, set the seasonal rhythm, drove the tides, paced the slowing of the day. And then Theia sank inside the Earth and stayed, and from the bottom of the planet has been nudging volcanism and tectonics for 4.5 billion years. The impactor is still here. The impactor never left. Close your eyes on that if you are settling into sleep. Let the image settle. Two masses of another world, sitting in the dark far beneath your feet. Every time a mantle plume rises and makes the ground shiver somewhere far above, the question of whether that material at the root of the plume is Theia is not yet answered. But the question is now being asked, carefully, with precise instruments and careful mathematics, by people doing real science. And the possibility, live enough to make it into nature, is that the body that built the moon left a fragment of itself at the center of the Earth and never fully dissolved. That is the final thread. Theia struck the young Earth. In the first hours, the iron cores merged and the surface became a glowing cloud of vaporized rock. In the first centuries, the debris outside the Roche limit coalesced into the moon, probably within decades or a few thousand years at most, geologically instant. The moon retained the tilted orientation of the combined system and has been holding that tilt stable, gently, across billions of years, damping the chaotic wandering that would otherwise have produced wild climate swings. The tides built by the moon slowed the 5-hour day into the 24-hour day. The early enormous tides may have helped shape the conditions in which the chemistry of life organized itself, though the connection between tide and life remains a hypothesis, not a certainty. And beneath all of this, at the core mantle boundary, The densest pieces of Theia's mantle may have been sitting since the first millions of years, still distinct, still identified by seismic waves as something not quite like everything else. The Moon is now at 384,000 kilometers and climbing, 3.8 centimeters every year. The axial tilt is 23.4 degrees, rocking gently through its 1.3-degree range, the seasons stable, the planet calibrated. The day is 24 hours, and still very slowly growing. And somewhere beneath Africa, and somewhere beneath the Pacific, in the absolute dark, and at pressures and temperatures that exist nowhere else in our experience, 2 continent-sized masses are there, still as they have always been. You might wonder, lying here, what becomes of all this? The Moon receding, the day lengthening, the blobs at the bottom of the world. It is in the nature of things that began violently to proceed quietly for a very long time before arriving somewhere new. The Hadean eon was noise and heat and vaporized rock and a 5-hour day and a moon filling a third of the sky. The world we have now is the long, slow exhale of that moment. The temperature has been falling for 4.5 billion years. The Moon has been moving away for 4.5 billion years. The blobs have been sitting, unmixed, for 4.5 billion years. There is something in that span that resists easy comprehension, but which, when you stop trying to comprehend it and simply allow yourself to be in proximity to it, produces a particular quality of quiet. The kind that comes when you understand that the ground beneath you is very old and very deep, and that the processes shaping it are very slow and very large, and that your life and everything in it is happening inside those processes, nested inside them, carried by them, in a window of time and stability that was opened by violence and maintained by distance, and will eventually close again when the Moon is far enough away. For now the Moon is exactly where it is, 23.4 degrees, 384,000 kilometers, 3.8 centimeters per year receding, measured by the laser light bouncing off the reflectors that were set there in another era, by people who understood that the Moon was once much closer and wanted to know exactly how fast it was moving away. They found the answer. It is leaving slowly. Slowly enough that the window, for all practical purposes, remains open. Stable enough that the seasons will continue to cycle, the tides will continue to move the water, the day will continue at its length within any span of time that biology can care about. Whatever happens next, in the far future, in the story of this solar system, it arrives in its own time. The collision happened once, in a moment that lasted perhaps a few hours when the actual contact was made, and the reverberations of that moment have been spreading outward through time ever since. The Moon above you is a reverberation. The 24-hour day is a reverberation. The seasons are a reverberation. And perhaps 3,000 kilometers beneath where you are now, something of the body that caused the collision is a reverberation too, sitting quiet in the dark, having done its work and come to rest. There is a particular peace in that if you let it arrive. The universe does not build things gently. It crashes bodies together at kilometers per second and vaporizes rock and melts iron and throws debris into orbit and then, over billions of years, very slowly builds something livable from the wreckage. The Moon was built from wreckage. The tilt was set by wreckage. The stable seasons and the tidal rhythms and the 24-hour day, all of it came from something that, had you been present for it, would have been the most terrifying event in the history of this planet. A world ending, and a world beginning at the same moment, in the same collision, with the same debris. And you are here, the product, in the most literal possible sense, of everything that followed from that moment. The stable seasons allowed the stable ecosystems. The stable ecosystems allowed the long evolutionary experiments that produced, eventually, complex animals and nervous systems and whatever it is that you are. Your body's biological clock is tuned to 24 hours, to the day that the moon built by slowing the spin. Your seasonal rhythms, the way your body responds to longer days and shorter ones, to warmth arriving after cold, all of that is downstream of the impact. The machinery that the collision installed is still running in you, right now, in ways that require no awareness and no effort. Just the quiet continuity of a process that started 4.5 billion years ago and has not stopped. The moon is above you. The blobs are below you. The tilt is holding at 23.4 degrees. The day will be 24 hours long when you wake. What happened in the Hadean is not past in the way that most of the past is past. It is present. The consequences of that collision are not history. They are the structure of the present moment. They are the length of the day and the cycle of the seasons and the angle of the sunlight through your window and the rhythm of the tides on every coast. The catastrophe is over. What it built is what you live in. Deep thinkers began this story with a morning on the Hadean Earth, a 5-hour day, a moon looming enormous and close, dragging walls of water across a world that had never known anything living. The violence of that moment was real, and the scale of it was beyond anything in our ordinary experience. And yet the thing to hold on to, as sleep settles in, is not the violence but the yield. What came from it? The quiet, improbable, enormously fragile and enormously durable machinery of a livable world, assembled from the debris of the most destructive event in this planet's history. Theia is inside the Earth. The moon is overhead. The tilt is steady. The day is long enough. The window is open. Let the deep thoughts settle, and let yourself sink with them.